Today we're going to talk about reaction rates and in particular how the stoichiometry of an equation can help you relate the rates of appearance and disappearance of the various species in a chemical reaction. Recall that when we're talking about the rates of a chemical reaction, we can look at these in terms of the change in the concentration of products or reactants over time. The concentration of the reactants is typically decreasing, and the concentration of the products is typically increasing. We can use stoichiometry to relate rates of formation or decomposition of the various species in reaction to each other. In other words, if we're given the rate for one species in the reaction, we can calculate the rates for the other species in the reaction using stoichiometry. Let's take the reaction A plus B reacts to produce C. We can get the following three reaction rates. Notice that the first two have a negative sign in front of them because they're being used up. Since rates are positive, we need to correct for this, and we put a minus sign in front of them. The third one is positive because C is being formed. The relationships between the rates of these species are very straightforward. For every mole of A that is used up, 1 mole of B is used up, and 1 mole of C is formed. But when our reactants and products have coefficients, it gets a little more difficult. Take a look at this example. We react 1 mole of A with 3 moles of B, and this produces 2 moles of C. We know that B decreases 3 times as rapidly as A does. We know that C is produced 2 times more rapidly than A decreases. To relate these to each other, we can divide each change in concentration for a species by its coefficient like this. Or more generally, for an equation where the coefficients are little a and little b, and our species are big A and big B, we can relate the rates to each other like this. So here's an example. The oxidation of ammonia is represented by this equation here. Say that it was found that the rate of formation of nitrogen was 0.27 moles per liter per second. The first thing that we are asked to do is write the rate expression for the reaction. To do this, we are going to look at the coefficients in front of each species. We are going to take the reciprocal of those and put them in front of the rate expressions for each individual species. And we have negative signs in front of the expressions for ammonia and oxygen because those are our reactants and they're disappearing. Second thing we are asked is at what rate water is being formed. So we're given the rate of formation of nitrogen is 0.27 moles per liter per second. We're going to use our rate expression to relate the rates of nitrogen and water like this. In order to find the rate of formation of water, we're going to do a little algebraic manipulation here. Then we're going to plug in our value 0.27 moles per liter per second. And we get 0.81 moles per liter per second. Next, we're asked at what rate ammonia was being consumed. Now, we have to relate the rate of formation of nitrogen with the rate of disappearance of ammonia, and we can do that like this. We'll use a little bit of algebraic manipulation. And then we'll plug in our value for the rate of appearance of nitrogen and get out our calculator, and we get 0.54 moles per liter per second. Remember, this minus sign just tells us that ammonia is disappearing, but we know that our rate is positive because rates are positive. In summary, the rate of change of a reactant and product concentrations are determined by the stoichiometry in the balanced chemical equation.